Next, we have Jingxiang Wu here from Oxford, who's going to be telling us about three-dimensional topological orders labeled by Seifert manifolds. Okay. Go for it.
Okay. Thank you very much for the invitation and opportunity to speak here. I'd like to talk about a recent work I did with Federico and Sakura, and some work in progress. So just to dive right into it, the main message of the talk is trying to draw your attention to this interesting correspondence we have proposed between MTC on one side and a choice of three manifolds, which I call M3, and a choice of group. I will explain all those symbol means later, but idea is that whenever you have a MTC constructed this way, there should be a geometry constructed this way and vice versa. And for simplicity, I will take the group to be SLNC here, but it should be generalizable to other cases. Just on the level of these formulas, it's rather obvious. They are at least labeled by the same set of data. I have n components, and each of them is labeled by a pair of integers, p and q. And there's a capital N here and capital N here. Okay. And on the geometry side, what's important is try to study the flat connections on this space. And this whole proposal is heavily inspired by a series of papers. So just first, I will try to remind you how Seifert manifolds look like. It's a quite simple construction of three manifolds. So you start from a trivial vibration of a circle bound over a Riemann surface. And what you do is you take out some solid torus, and you glue it back in by performing some twist. So this is known as a dense surgery. After you do that, what you get is this manifold. So there are n small disks you take out here that correspond to the number of pair of integers here. And for each little solid torus you take out, you need a pair of integers p and q to label how much you twist. And more precisely, it gives you which cycle is contractible in this space. This might seem rather simple looking, but it turns out that this is quite general. So there's a Thurston geometrization classification, and there are 8 of them. It turns out 6 of the geometries can be constructed this way. For this talk, I will only look at genus 0 when the base is a sphere. So on the other side of the correspondence, we have MTC. This is a heavy subject with lots of machinery. Unfortunately, I don't have time to explain that, but it turns out, well, for this talk, we don't need lots of them. And for each of the data we have in the MTC, it has very obvious physical meaning. For example, the object of this category corresponds to anyons. You have a particle going forward. And there's an S matrix that corresponds to how different anyons braid with each other. And there's a T matrix that corresponds to the spin of these anyons, basically. It turns out there's you need finer data to fully specify this category, but I won't mention it here. It's very important for MTC to have an S matrix that's modular. If you remove that, this is called pre-modular categories. Okay. So MTC is very important because it's a mathematical language for 3D GCAPTs. So whenever you want to understand 3D gapped phases of matter, you need MTCs. And if you put a boundary, it also has very close relations to 2D CFTs, quantum groups, etc. There are 2 particular theorems that make the study of MTC very nice. One thing is called octoniarity rigidity. This basically says MTC is a discrete object. There's no continuous parameters. So another theorem that's very important is called rank finite theorem, which says at any fixed rank, rank is the number of anions. At any given number of anions, there are only finitely many possible MTCs. So this is the nicest possible scenario where you can just try to imagine we should be able to classify the MTCs, right? This is a finite list. And you can try to do that. So you start from a possible fusion ring, and you try to write down all the possible equations that is satisfied by the data. That are known as pentagon and hexagon relations. Those are the equations. The details don't matter here. But the main message here is there are a lot of symbols. For each of the indices, it's taken in this set of anions. So there's a lot of symbols and a lot of equations to solve. And what's worse is the solution don't always exist because there are many more equations than variables. So just to show you the decades of effort that's put into this endeavor, starting from 2000, and people are making some steady progress in understanding like low ranks of MTCs, but the full data is only understood up to rank 5. And further ranks, we only have part of the data, known as modular data, an S and T matrix. So this is a very complicated task. The approach we are taking here is try to say maybe there's some alternative perspective that we can try to understand this space of MTCs by doing a geometry question. So this is the construction of MTC. We have it here, right? So what is each of the building block? This is known as the quantum group category. So it's associated to the representations of quantum groups at a specific level, a root of unity, and you do the simplification. Okay. But all that matters here is this is relatively understood category, and it's very similar to Chen summons. Okay. So for the purpose of the talk, it's okay to assume this is the Chen summon theory. And in particular, for SLN, you have a Z in one-form symmetry. But a warning here is this category may not be modular. It could be pre-modular. Okay. And what is this product here? So because each building block has a Z ingredient, it's rather natural to put them together by defining this graded product. So whenever you have a graded category, you just multiply them together between each graded component, and you sum of them together. This is a subcategory of the usual product. So this is a very naive operation you can do, and it has been proven that this operation is rather nice. It preserves the pre-modular structure. It's basically, preserve all the structure you want except the modularity structure. So each building block is not necessarily modular, and this operation does not preserve modularity either. So it turns out the hardest part is try to determine which category like this is modular. But otherwise, this is super explicit. You just need to plug in numbers. Okay. So just bring back the geometry side. We have this. Now, suppose I haven't explained why this is a correspondence, but suppose this is true. It turns out it gave us some strong hint on the structure of MTCs. For example, there's a natural geometry associated to this. And Seifert manifold is much more better understood than MTCs. And you can try to ask, okay, this is a very contrived construction of MTCs. How general is it? So we just try to, because this is rather well understood, we just plug in numbers and see, compared to the list of classifications I showed you earlier, and which MTCs can be constructed this way. It turns out, up to all the rank 5, which has been classified so far, all of them can be recovered, both unitary and non-unitary. Okay, so it just give you some encouraging news. Maybe inside this large space of MTCs, a very big chunk of this is captured by this. And the hero of this game is this graded product, which I mentioned is not a topological operation. It's not a gauging or ungauging any sense because it doesn't preserve modularity. So where do we use the geometry properties of the MTC? It's asking us to solve the flat connections on this space. Flat connections, mathematically is like this, but physically it's very simple, right? You just, for any cycle, you will try to associate a matrix, which is a monodromy. And the monodromy has to satisfy some relations. They have to come together into this pi1 group. So this is a bunch of SL2C matrix you have to solve. But this matrix equation is also hard. It's much simpler than the Pentagon equations, but it's still very hard. And actually, it's not only known when small n is 3, or when I have 3 fibers, and the group is SL2C. Beyond that, very little is known. So that's why most of the effort of this project was spent on trying to understand the flat connections on this space. After lots of manipulations and tons of numerical checks, we arrived at this conjecture, which basically says there's a large part of this flat connections that's very easy to understand. So there's a particular type of, excluding some special cases, you think of this matrix, you exclude the case where the eigenvalues could be repeated. You forget about them. It turns out the remaining case have a very nice structure. The symbols, I haven't explained them, but the message here is they look exactly the same as how we constructed MTCs. You have a bunch of sets, and they are graded by Zn, and you just tensor product all of them, and you have the Zn grading structure in the end. And for each element here, there's a corresponding element here, which labeled flat connections. Okay, so this is basically so I have to say a caveat, which is the space of flat connections is rather complicated. There are some continuous parameters. And what we are answering here is the pi0 of this space. What are the kinetic components of this? It could be this kinetic component only have one point. It could be a two-sphere. That part, we are rather ignorant about that. Okay. So we can quickly do some checks to make sure we're not being crazy here. There are some cases where two set of integers actually secretly label the same set of Seifert manifold. They are different, but and if the proposal is going to work, they have to give you the same MTC. If you plug in the numbers and do some checks, it turns out they are the same. Okay. Another thing is, as I mentioned, to try to understand when is it modular is a very hard question. You can try to do some exercise and figure out which MTC is actually modular. It's a very hard like number theory question. But it turns out it has this simple answer. It's modular if and only if the first homology group is trivial, which is much easier to compute systematically. And there are many data we can associate to this geometry. And there are many topological invariants we can try to match. One of the important topological invariants is Chern-Simons invariant, which is, we are starting flat connections, right? You're plugging in the classical Chern-Simons action. This is a topological invariant. And what it corresponds to on the MTC side turns out to be the spin of the anyons, which is nice. You can try to compute them. It turns out they work. Okay. So let me conclude here. So the idea is that there is this intriguing correspondence between MTC and Seifert geometries. in particular the flat connections on the Seifert geometries. It teaches us things on both sides. Because we don't know much about the space of flat connections, we have to use numerics in many cases. But we do understand something about MTCs, and it turns out the knowledge of MTCs gave us some new conjectures about the space of flat connections. And on the other side, we can also try to use this machinery to construct new MTCs that we didn't know before. But obviously, this is a very special case. We only look at SLNC. We only look at when the base manifold is two-sphere. It can try to generalize this to more arbitrary three-manifold. And there are many operations you can do to geometries by cutting and gluing. This is not obvious what it corresponds to on the MTC side. Okay. And it's not obvious either what is unitarity structure of the MTC on the geometry side. Okay. With that, thank you.
Thanks for the talk. What motivated you to look for this conjecture in the first place? Like, why would you come up with this idea at all?
So the motivation was from this paper, where they started from the 3D correspondence and conjectured a very similar construction.
So you think there's some stringy origin to this? Some 60.
It seems to work in a special case where they started. They only started the small n is n equals to 3 and SL2C. It seems to make sense, but there's no obvious way at all to extend it. You can try to extend in any direction, it doesn't work.
I see. Thank you.
Yeah.
Thanks. Can you help me? Can you say more about your conjecture for modularity, right? You say it's H1 valued in Zn.
Yeah.
Is zero. So that's super restrictive. That's like rational homology spheres. No?
Can you say that again?
Those are like the rational homology sphere, I think?
Yeah,
So
exactly.
that's a very restrictive subset of the Seifert manifolds, right?
Yes.
And so there you can classify, and that's where you can find a match rank by rank. I mean, of the MTC.
Yeah.
I see.
The geometry question is much easier than the MTC side. Yeah.
Right, indeed. And then I guess if that conjecture holds, then you don't need to look at higher genus either, right? Because that would give some extra factors of Zn. Every genus would add.
Yes, but then there's obvious question: what if this is non-trivial? What does it mean? It turns out there's also a very nice story.
Okay.
It's on itself, it's not modular, but you can make it modular by doing something.
Thanks.
Sorry to make you run. Thank you. I was curious about where does the circle fibration on the Seifert side enter into the properties of the MTC? So if you were to relax the circle fibration, would you relax some of the categorical properties on the other side of the correspondence? Is there something to say?
Yeah. I don't know. That's a good question. I don't know. I mean, if you look at the equations, that's why it make it work. There's all the fibers have the same direction, and that's common to everything. That's what's giving you this Zn structure. The monogamy of that fiber, when you multiply n times, like V1, that's the Zn structure. I don't know.
So I guess I'm thinking, like, if you think about the 3D correspondence as being the motivating principle there, Seifert manifolds are just a special case, and you can think about it for general topological three manifolds.
Yeah, indeed, yeah.
And then you might expect some other kind of categorical structure, but I don't know if you...
Oh, yeah. If you're asking whether it can be generalized to non-Seifert cases, the answer is yes. There has been some starters.
And what generalizes on the MTC side? It's no longer an MTC, but it's...
It is still, for example, some people have started the torus bundle, which is not a Seifert, and it's still MTC in many cases.
I see. But there's no such MTCs of rank less than 5, since you said you had all...
Oh, it could be like different construction give you the same MTC secretly.
I see.
Yeah, it's not one-to-one, like, yeah.
Okay, awesome. Yeah, thank you.
Okay, I think we should thank the speaker again.